Hello and good day everyone. We are from Group 1 and today we will be presenting about our project which is the design and structural analysis of a spaghetti bar under bending load. Let's start our presentation with the introduction of this project. Firstly, we have the background of the project. This project applies the principle of mechanics of materials through the design and testing of a spaghetti bar. A 30 cm long and 1.5 cm thick spaghetti bar with a specified cross-sectional shape is fabricated using uncooked spaghetti. The bar is subjected to a gradually increasing bending loads until failure to evaluate its structural behavior. The project analyzes the shear force, bending moment, and allowable normal stress while enhancing practical engineering and teamwork skills. Secondly, let's look at the objective of the project. So the objective of this project is to design and fabricate a 30 cm long and 1.5 cm thick square spaghetti bar for a bending test. Secondly, it is to investigate the behavior and failure of the spaghetti bar under a gradually increasing bending load. The third one is to determine the shear force, bending moment, and allowable normal stress based on the experimental results. And lastly, it is to apply the principles of mechanics of materials by comparing theoretical calculations with the experimental behavior of the bar. Now, let us look at the model fabrication method. To create the bar, you are using the Kimball spaghetti, but you are free to use any spaghetti brands that you want to use. And then we were using the sellotape and also super glue. So now I'll be explaining about the methods that we use. Firstly, the spaghetti strands were cut and arranged to form 30 cm long and 1.5 cm thick square bar. Secondly, sellotape was used to hold the spaghetti strands together and maintain the square shape during assembly. Thirdly, superglue was applied between the spaghetti strands to bond them into a single rigid structure. And lastly, the glued bar was left to dry completely before being tested under a gradually increasing bending load.
So this is our process of creating the model. First, to make it become a single layer, we use a super glue and also tap to grab all of the spaghetti become a single layer. After that, we combine all of the layer together become about 3-4 layer model, which is long 30 cm and also the thickness is 1.5 cm. So after that, from the video, we use the ruler to measure the length and also the thickness of the model. So we can clearly see the thickness is 1.5 cm and also the long is 30 cm. Then, after all our model already prepared, we will start to test the model with the selector loading. The distance we use for the spaghetti lie on the table is 2 cm for each side. Then, we will add 50 ml of water to the water bottle until the spaghetti reach its maximum loading and then break. Then finally, the spaghetti bread at 2.15 kg of water adding.
Okay, next we move to the calculation part. First, we draw the diagram of to show where is the separation and also the load located. After that, we can draw a feedback diagram to find all the unknowns. First, we use the sum of the moment at point A is equal to 0. Then we can easily find the separation MB. After we get the separation MB, we can use the sum of force in y direction equal to 0 also. Then we can find the separation at A. After we get the separation of A and B, then we can move to the further step for calculation for the cell and moment diagram. Who will cut it into uh, two sections. Then we can find the function of moment and also the value of cell stress. Okay, next, after we finish the calculation for all the five roots, we conclude it in this table, and we will use this table to the further drawing for the cell force and also bending moment diagram. And this is the cell and bending moment diagram for loop 1 and loop 2. As you can see, the shape of the almost same is already different in the volume of the moment, maximum moment, and also the maximum cell force. And then we move to the cell and bending moment diagram for loop 3 and loop 4. They also have the same shape as loop 1 and loop 2, and their volume of cell force and moment also increase because of the mass of loop increase. Okay, last one. This is the cell embedding moment diagram for the loop 5, which in this root our bend is broken, that the maximum cell force of it is 10.546, and also the maximum moment of this is 1.371. Okay, after we finish all the cell and the bending moment diagram, we move to the calculation for allowable normal stress. First, we drawing the side view for the bed pin to our reference, and then we use it for find our initial and also the C. Therefore, we can use the I and C we find to find the S. After we get the S, we can use it to find the ultimate stress, which is the maximum moment derived by S. And we can get that the volume of our ultimate stress is 2.44 megapascal. And by using the suggestion safety weight factor, which is 1.5, we can use it to find our last target, which is the allowable stress, which and we can get the value is 1.62 megapascal. And this finish all my part. I will move to my other team members. Thank you.
Moving on our last part of presentation, I will present the conclusion that cover both, which is summary of findings and reflection of our project. For the summary of findings, the objective of this project was successfully achieved by designing, fabricating and testing a 30 centimeter long and 1.5 centimeter thick square-shaped uncooked spaghetti bar under a 3-point bending test. The spaghetti bar successfully withstood a maximum load of 2.15 kg, which is 21.092 Newton before fill. The maximum bending moment occurred at the midpoint of the 30 cm spaghetti bar, which is center of the span with a value of 1.371 Newton meter, that producing an ultimate normal stress which is sigma max of 2.44 megapascal. Based on the required safety factor of 1.5, the allowable normal stress for the structure was 1.63 megapascal. Overall, this project demonstrated the relationship between load, bending moment, and normal stress in structural members. It also highlighted the importance of proper fabrication, accurate calculation, and teamwork in producing a stronger and more reliable spaghetti structure. For the reflection of the project, it enhanced understanding of bending behavior and stress analysis. Other than that, we can learn the importance of accurate fabrication and material arrangement. Also, improve teamwork, communication, and problem-solving skills. For the future improvement, we use a more precise mold and achieve a more uniform spaghetti arrangement for the better structural performance. That concludes Group 1 presentation. Thank you.